Hey there! In this video, I'm going to introduce to you the third big idea in the rotation unit of AP Physics C, which is torque. And we're also going to introduce how that can be used for rotational statics, kind of introducing this extra component to the statics that you would have learned in the forces unit. Before we do that though, I would like to give a word for our sponsor today, which is the cross product. It is a product that is really the cousin of the dot product. It's kind of the same idea. However, there is a pretty significant difference. Cross product, just like dot products, are a way of multiplying two vector quantities. However, contrary to a dot product, which produces a scalar quantity, cross products produce a vector quantity. The big difference here is in what the cross product is actually producing. I'm going to put an animation up above where my web camera is that shows kind of what we're getting out of the cross product. And in addition to that, there is a handy hand trick that you can use to represent a cross product that you'd get out of two vectors. Over here, really with your right hand, and always your right hand, only your right hand, the direction of the cross product can quickly be determined based on your pointer finger, so your index finger, your middle finger, or sometimes the palm of your hand, or all three of your fingers below your index. And you want those two to be perpendicular to each other, like you see here. And when you have that set up, the result of the cross product is going to point in the direction of your thumb. This is a trick that plays a huge role in not only rotation, but a lot of the concepts in electromagnetism as well as electrostatics. We're going to be using this quite a lot in the future, so it's helpful to get used to it now. And we are going to be using it later in this video. The last thing we need to know about the cross product is how we actually calculate it, because we have this weird scary X here, and all we really know right now is that it's stealing yet another multiplication symbol away from our dwindling supply. A cross product can very quickly be calculated by taking the magnitude of vector A times the magnitude of vector B times the sine of the angle between them. This is very similar to the the dot product, which would have you multiply those same two magnitudes, but with the cosine of the angle between them. Really, mathematically, the thing to take away here is that cross products produce a vector that's perpendicular to the plane containing the two vectors A and B. And that can be very helpful outside of physics, especially in areas like linear algebra, where you're having to create lots of perpendicular vectors if you're making 3D spaces and stuff. Physically though, and intuitively, in physics, usually the purpose of the cross product is really just to have a function that tells you how perpendicular the two vectors are to each other. If you want something to be maximized when something is perpendicular, you use a cross product. So now let's take a look at torque itself. This is really the first physics part. So when thinking about torque, we're again continuing that tradition of really just making rotational counterparts to linear quantities. So the linear quantity of force is understandably a huge physics concept. So it makes sense that we would want to try and make a rotational version of that. So force conceptually is what gives an object acceleration. So then the rotational quantity for force, which we call torque, is naturally what gives an object angular acceleration, which is a quantity we've already talked about. So in describing torque and understanding it, I think on a personal level, the best way to truly understand how this thing works is to think back to your skills in opening a door. I hope that you have at least some experience with this, or if you don't, well, hopefully you have at least a door somewhere around you in your general area, and you can go and try some of this stuff out for yourself so that you get a feel for where torque is applying and some of the models behind it. So I'm going to use this example here of a door, and I want to highlight three key indicators. So first off, we've got this hinge. Most things in rotation are going to rotate about some central hinge. So that's this thing right here. Next is this distance r. This r value is really an indication of how far away from the hinge the force is being applied. So in this case, the force is being applied a distance r away, but if the force were being applied over here, it would be applied a distance r divided by 2, or r over 2 away from the hinge. The last thing that isn't really shown here, but is still pretty important, is the angle. So the three factors that really influence your ability to open a door are the magnitude of the force applied. The more force you apply to a door, the harder it's going to swing open. The next thing that matters is the location of the application of the force. This is important because if you try to open a door by pushing on it really close to the hinge over here, you're going to find that it's a significantly different experience than if you were to try and open the door at the usual place next to the doorknob. And the last thing is the angle that the force is applied relative to the distance from the pivot or the hinge. This is especially evident if you try to apply the force this way on the door. Go to a door near you, try your best to open a door by pushing on the door towards the hinge. If you want to pause and go try it out, be my guest, or you might automatically know through intuition that this is no good way to open a door at all. The most optimal way to do it is to push on it perpendicular to the door. That's sounding weirdly familiar, but we'll get back to that in a second. Those are the three key things, so let's make a model based off of it. First off, let's think about just a rough description of tangential force versus rotational torque. A good way to describe the tangential force is a push or pull that causes motion. So then rotationally, torque should naturally be a push or pull that causes rotation. Really the main difference here is that you can have both of these happening at once. So you can have a tangential force that's moving an object in a linear space, meaning it's just traveling in one direction. At the same time, that object could also be rotating. Let's think about the equation that could model all of the stuff that we're talking about here. So torque, represented by the Greek letter tau, can generally be defined as the cross product between the distance away from the hinge with the force that's being applied. Now, this should come as no surprise because that angle plays a pretty key factor here. A cross product is maximized when two vectors are perpendicular to each other. It just so happens that empirically it works out that way, and the cross product is the perfect function to represent that. But we have a better way to write this that's a little bit less intimidating looking, which is the distance away from the hinge times the force being applied times the sine of the angle between them. This is the most common way that you'll find to solve for torque, and a lot of the time in solving for torque, the sine theta is going to go away entirely because oftentimes, especially in physics classes, the angle between the two is going to be 90 degrees, as seen in this picture here. Two things to note here. First, torque is expressed in units of Newton meters. I have a double asterisk here to further elaborate on that because you may see this Newton meters and think, hey, isn't that joules? Which, I mean, in a way you're right. It is expressed in the same units as energy, but strangely it is not a form of energy, even though it has the same units. I'm not going to elaborate on that too much more, but just know that torque is not a form of energy like work is. So the last thing here is that, again, in the spirit of rotation, since we've introduced a new quantity now, we can take that quantity and plug it into some of our translational formulas to get a rotational version. So what better equation to start with than the legendary Newton's second law, that the sum of the forces equals the mass times the acceleration of an object. So rotationally, as you could probably guess, that's going to end up as the sum of the torques equaling the moment of inertia, which remember is the rotational equivalent to mass, times the angular acceleration of the object. So in this case, we were able to swap out all three letters for rotational terms. It's getting pretty exciting. If you want to justify this, just know that we could have something like r times f equals a pretty standard moment of inertia would be something like m times r squared. And angular acceleration, if you remember, would be the linear acceleration divided by r. So it would be a over r. So if you note here, this cancels out with one of the r squareds, and then this r would divide over to the other side to cancel that, and you would get to f equals ma. So everything checks out. We're all okay. The world does not burn down, and we can proceed to do some fun stuff with this new fancy equation. The last thing I want to remark on is the direction of torque, because this is the thing that usually gets people's goat here. So like force, again, torque is a vector quantity. You can determine the direction of torque with the right-hand rule, like we mentioned earlier. So according to the right-hand rule here, the direction of the torque acting on the door in this picture here would be what? Pause the video and try it out. Remember, you want your index finger perpendicular to your middle finger, or to your palm, or to these fingers here. And then you want your thumb pointing in the direction perpendicular to both of those. So try it out really fast. So if you try this out, you want to aim your pointer finger in the direction of the vector r, and then you want to point your middle finger in the direction of the vector f. And when you do that, from your perspective at least, you should note that, weirdly, the direction of the torque acting on this door is out of the page, or I guess out of the screen in this case. Now that seems very counterintuitive, because you may be thinking, well, intuitively, this door is like rotating around still in the plane of the page. It's not like it's like swinging out of the screen and shattering the glass. And you would be right. And part of the reason it's set up this way is because, well, the direction of rotation can really be broken down into two different styles. So, and like a slightly easier way to describe the direction of the torque can sometimes be to describe it as counterclockwise. Now, by counterclockwise, I mean specifically in this situation, where if you imagine that a force were to be applied to this door, or you like put your pencil on your desk and try this out, applying a force in that direction is going to cause it to rotate, well, counterclockwise. So if you think about the only other option here, it would be clockwise. So you have two options, two directions that this thing could possibly go in, positive, negative. And so really the only other option that we have to work with here is maybe into or out of the page. Two options. And so while intuitively the into out of the page direction doesn't make a whole lot of sense, just know that it's kind of a mathematical thing. So from here on out, I am going to be describing the direction of torque as counterclockwise or clockwise. I think it makes a bit more intuitive sense and it's a little easier to visualize. So in that same vein, by convention, we're going to call counterclockwise torques positive and clockwise torques negative. That's really all of the crazy stuff regarding torque itself. And so now we're going to move on to figuring out how to apply some of this stuff. And we're going to start with rotational statics. So statics, if you remember from way back in a forces unit somewhere, involves the dynamic of stationary or static objects. Statics problems always assume the very convenient thing, which is that acceleration, ideally, is 0. I say ideally because statics plays a huge role in something like bridge building, where you want a very clearly static object that's safe for you to traverse across. If you don't have a static bridge, or something is not equaling 0 on the bridge that you're on, you are in for a very bad day. So, for an object to stay in true static equilibrium, it's got to meet two conditions, according to Newton's second law, which, remember, we now have two versions of. Firstly, the sum of all the linear forces need to add to 0. So this means like any forces that are up or down need to cancel out. Any forces that are left or right need to cancel out. And then now we have this new condition that the sum of all of the torques acting on an object also need to cancel out. That means that any torques that would cause an object to rotate counterclockwise need to cancel out with any torques that are causing the object to rotate clockwise around a certain pivot point, usually like a point of failure or an attachment point or something similar. Let's go ahead and apply this to an example. So in this example, our character is an adventurer who looks mysteriously like Indiana Jones, who encounters a 150 kilogram, 10 meter long plank that lies flat on a cliff edge, where 3.5 meters of that plank are over the edge of the cliff, as shown here. So we've got this 3.5 meter distance where it's hanging over the cliff edge, like that. And then we also have some weights that we can compute. So let's look at the plank first. So the plank, if you remember back in the momentum and impulse unit, when we're covering center of mass, we tend to generalize all of the mass of an object into its center of mass, to a singular point. Since this plank looks pretty uniform and there's nothing really telling us that it would be otherwise, we can go ahead and assume that this plank's weight can be centralized to the center down here. So with the plank being 150 kilograms, if we multiply that by 10, or 9.8 to roughly get its weight, the weight of the plank, which I'll call WP, is going to be about 1500 newtons. Okay? And then our adventurer over here also has a weight that we need to write down. And again, this one's going to be bearing down, just where they're standing. And this weight, let's call it WA, is going to equal about 9.8 times 100, or 10 times 10 times 100, which will be 1000 newtons. So that's all of the stuff there. So let's continue. So this person walks out onto a plank to retrieve a magic object of negligible mass. So that's nice. At least we don't have to worry about the object. So the question is, how far can the adventurer go from the edge of the cliff? That's this little distance X here, before the plank tips over, which would not be good. So our goal here is to figure out the distance from some pivot point, which, if you think about it in this case, we're not really given a hinge like on that door picture from earlier, but we could say that, if we imagine this plank to rotate about one singular point, it's probably going to be the cliff edge right here. If they walk out far enough, the plank is going to rotate about that point and fall down this way, and then our adventurer will meet their demise. So let's figure out how far they can go before that happens, so we can warn them. So first off, we should remind ourselves of a couple of things. First off, in order to calculate torque, remember that it's going to be the distance away from the pivot times the force involved times the sine of the angle between those two. Secondly, we've got Newton's second law for rotation, which tells us that the sum of all of the torques in this case need to equal 0, particularly for a statics problem. We'll worry about the other Newton's second law later. Our goal with this, and with any rotational statics problem, is exactly like a regular statics problem. We need to figure out the torques that are going in the clockwise direction, as well as the counterclockwise direction, and ensure that those are going to add up to 0 here. So let's think about which direction each force is going to be turning us in. This force here, the weight of the adventurer, if you imagine it intuitively, is likely to cause this plank to rotate clockwise, like that. And that's usually the symbol I use for it. Conversely, the weight of the plank over here is keeping the plank from rotating about that cliffside. As long as this weight here is enough to support whatever's going on over here, the plank isn't going to rotate. So this weight over here is a counterclockwise torque. It's going to cause it to rotate the other way. So these two weights are opposing each other. So let's calculate our torques really quick. So the torque of the adventurer is going to equal the distance x away from the pivot, which we don't know, that's what we're trying to solve here, times the force involved, so that's going to be times 1000 newtons. And then the sine of the angle here is going to amount to 1. Why? Well, remember, distance x is going out this way, to the right. The weight is going down. So those two vectors are perpendicular to each other. Sine of 90 degrees, perpendicular, is 1. So we can leave this as it is right here. Then the torque due to the plank on the other side is going to equal, well, we need to figure out this distance. That's going to be a little complicated. So taking a look over here, if the distance from this far end of the plank all the way to where the weight is being applied, this distance is about 5 meters. So we have kind of this sectioned off into part of this being 3.5 meters. So 5, or the difference between these two, 5 and 3.5 meters, is going to be 1.5 meters right here. So the distance from the pivot point that the weight of the plank is being applied is 1.5 meters. And then the force that the plank's weight is applying is 1500 newtons. And once we have that, we are ready to proceed to round 3. In order to round all of this out and figure out our distance, what we need to do is add our forces, our torques together, noting that they have opposite direction, and find the distance x that our adventurer can go. So with the sum of the torques equaling 0, we've got 1000x minus the opposing torque, which is 1.5 times 1500, and those need to equal 0. So if you do some rearranging here, you're going to find that x equals 2.25 meters. So this is big news for our adventurer friend. because if that treasure truly is at the very end of this plank, they are not going to be able to reach that treasure. If they do, if they get a little greedy, down the cliff for them. Not good. Let's try a different one. So example 2 follows our adventurer yet again as they come across another 150 kilogram plank. I don't know how this keeps happening. This plank is tied to 2 cords this time that hold it horizontally so that it acts like a bridge. The adventurer crosses the plank and is at this moment 8 meters away from the left side of the plank. So relative to this very far left side here, this adventurer is 1, 2, 3, 4, 5, 6, 7, 8 meters away. So the goal here is to determine the tensions in the left and right cords that are suspending this bridge. We're going to go ahead and assume that we have the same weights from last time. So there's going to be a force of 1,000 newtons bearing down right here. So we'll call that WA, and that's 1,000 newtons. And we're going to assume again that the weight of the plank is directly in the center, and that's 1,500 newtons. All right, so our goal here is to figure out the tension in the left side of the plank, or in the left cord. So we'll call that TL, and the tension in the right cord, which we'll call TR. And those are both going to be tensions pulling upwards, because otherwise this bridge would currently be plummeting downwards at a rapid pace. So in this problem, we're going to need to take advantage of both of our statics laws. So that's going to be the sum of the forces in the linear direction need to add to 0, and the sum of the torques about some given pivot point also need to add to 0. So to get started, I recommend in a problem like this that you always start with torques, and I have a very good reason as to why. In these problems, kind of like, again, when you're solving center of mass, you have a choice in what your reference point is. Meaning you can find the sum of the torques about any pivot point of your choice. There's no easily well-defined pivot point in this problem. So your goal should be to pick a pivot point in which you're eliminating a force. What do I mean by that? Well, remember that torque is defined as the distance away from the pivot times the force times the angle between them. The important thing here is the distance away from the pivot. If we have a choice in where that pivot point is, then if we choose a pivot point, like let's say this left side of the plank, that is at the location of a force that we don't know, we can simply count that as a write-off and say, we don't know the force, but we also don't really need to use it in this case. And in that way, it feels like a cheat code, but it's totally fine. So in order to figure out, let's say, the tension in the right side of the plank, that's exactly what we're going to do. We're going to choose our pivot point to be at this left side of the plank so that we get rid of TL. And that way we just have this force, and this force to figure out the torques of. On our diagram, I'm going to go ahead and list the expected rotation direction that each of these forces are going to cause. The weight of the plank over here should likely be causing a clockwise rotation relative to this pivot point right here. Imagine this is a door hinge. The weight of our adventurer over here should also be doing the same thing. It's going to be causing a clockwise rotation. The tension in this cable over here then is the sole thing that is keeping the system from rotating downwards. It should be pulling this thing, or at least opposing in the counterclockwise direction. This means that the torque caused by the plank plus the torque caused by the adventurer need to balance out with the torque caused by the rope over here. Let's get that in writing. The sum of the torques on this plank are going to be the torque caused by the plank plus the torque caused by the adventurer minus the torque caused by the rope going in the opposite direction. And all of those torques need to add to 0. Expanding this out a little bit more, well, the weight of the plank is going to be about 5 meters away from its left side. It's halfway across. So the torque of the plank should be expressed as 5 meters times 1,500 newtons, which is its force or weight. And again, the sine of the angle here is going to cancel out to 1 because all of the distances and forces involved here are perpendicular. So we don't really need to worry about the sine component here. So then the torque of the adventurer can be expressed as the distance, which is given as 8 meters, times the weight of the adventurer, which was 1,000 newtons. And again, that sine theta is going to go away. And then finally, we need to make an expression for the torque from the rope, which again, we don't know the force, but that's okay. That's our unknown in this equation. So the torque caused by the rope is going to be a total distance of 10 meters away times the tension in the rope, the force that it's applying. And all of those added together need to equal 0. So if you do some quick rearranging and you do the algebra to solve this, you should find, after all of that, that the tension in the rope equals 1,550 newtons. So having this force is going to make finding TL a heck of a lot easier. And we have two options now. We can either use torques again, and now this time place the pivot point at the location of TR, or we can use our other condition here, Newton's second law in the usual sense. And all we really need to do here is find the sum of forces, because we know that they need to cancel out to 0. So we would add the two upward forces, TL and TR, and subtract from them the sum of the two downward forces, 1,500 and 1,000. So doing that really fast, we need the sum of forces, which is going to equal TL, our unknown, plus TR, which we solved for, minus 1,500 newtons downwards, minus the weight of the plank downwards, and minus the weight of the adventurer downwards. And all of those need to add to 0. So plugging in our numbers then, we've got TL plus 1,550 minus 1,500 minus 1,000, all equaling 0. And so if you just rearrange everything, add them all up, you should find that TL equals about 950 newtons. And I barely had enough space to write all of that out. One thing that's interesting to note here is that TL is applying less force than TR. That sort of makes sense because most of the weight is distributed on the right side of this bridge. This rope is having to work a heck of a lot harder to keep everything stable than this rope is over here. And we can figure that out using all of the torques that we would have had to work with here. And we can figure that out with the torque methods that we've just introduced here. So that's a pretty good start, and we're going to be working with Newton's second law and all of its fun applications with torque next time. So I hope this video helped, and I will catch you on the next one. Peace.